Have you ever stopped to think about how we get a machine to understand something as simple as a cat? I mean, we can't just tell it, hey, this is a cat. We have to speak its language. And its language, well, it's all about numbers. Today, we're going to break down a really cool technique for translating our world into a format that machines can actually get their heads around. So let's just start with that big question. How does a machine actually understand the word cat? Well, the short answer is it doesn't. Not like you and I do, anyway. A computer doesn't think in words or fuzzy concepts. It thinks in numbers, cold, hard numbers. So our first job is to figure out how to bridge that gap. And this right here, this gets to the very heart of the problem. On one side, you've got us with our simple, intuitive labels, cat, dog, whatever. And on the other side, you've got what the machine needs, a super clear, totally unambiguous numerical format. The whole game is figuring out how to get from our side to theirs. So yeah, that brings us right to the core of this whole thing, getting fluent in a machine's language. How do we build that bridge from our words to its numbers? You see, this is one of the first rules of machine learning. It doesn't matter if we're talking about pictures of animals or, types of cars. Those labels, dog, cat, lizard, they all have to be encoded. They've got to become numbers, usually vectors of numbers, so the model can actually do its math and learn from the data we give it. And that leads us to a really clever and super common solution to this problem. It's a technique called one-hot encoding. So, what is it? Well, one-hot encoding is basically a process that takes our labels, like our animal names, and it turns each one into a special list, a vector that's made up of nothing but zeros and a single one. It's a super simple but really powerful way to represent these different categories. And the best part? It all boils down to just two simple rules. That's it. First, the length of that list, or vector, is always equal to the total number of categories you have. So 3 categories, your vector has 3 spots. Rule number 2, for any given category, only one of those spots in the vector is 1. That's the hot spot, and all the rest have to be 0. Okay, I know that might sound a little abstract, so let's make it way more concrete. Let's walk through an example with our animal friends: a cat, a dog, and a lizard. All right, so we've got our 3 categories: cat, dog, and lizard. Now, if we apply that first rule, what does that tell us? It means all of our one-hot encoded vectors are going to have a length of exactly 3. Simple as that. Now, let's try out that second rule. Let's just decide, right now, that the first position in our 3-part vector is going to represent cat. So, what do you think that vector is going to look like? Yup, exactly. The vector for cat becomes 1, 0, 0. That first spot is hot because it's the cat. So following that same logic, if we say dog gets the second spot and lizard gets the third, their vectors become 0, 1, 0 and 0, 0, 1. See? Each animal gets its own unique numerical fingerprint. No confusion. Okay, so far so good. But, the real world is messy. What happens when our world expands a little? Let's say we find a new animal we need to classify. Let's throw a llama into the mix. So this is our system right now. 3 animals, each with its own vector of length 3. It's a perfect, neat little world. But that llama is about to shake things up. So with the llama, we now have 4 categories. And what does our first rule say? It means the length of all of our vectors has to grow to 4. Our entire system has to adapt to this new reality. And here's exactly how that adaptation works. Check this out. See how the original vectors for cat, dog, and lizard have changed? A 4th spot, a 0, just gets tacked on to the end of each one. And that brand new 4th spot, that now belongs to the llama, so its vector becomes 0, 0, 0, 1, claiming that final hot position for itself. Now, here's a quick but really important point. We just sort of randomly put cat first, dog second, and so on. But that order, it doesn't actually matter at all. We could have made llama the first position and cat the 4th. The only thing that matters is that once you pick an order, you have to stick with it. Consistency is absolutely everything here. Okay, so we've gone through the how, but let's take a step back and talk about the why. Why do we go through this whole song and dance of turning words into these lists of zeros and ones? Why does any of this matter? Well, there are a few huge reasons. First, this is our translator. It turns our fuzzy ideas into a clear, numerical language the machine gets. Second, and this is so important, it stops the model from seeing relationships that aren't really there. Like, if we just use numbers like cat equals 1, dog equals 2, llama equals 3, the model might think a llama is somehow more than a cat. One hot encoding says, nope, they're all just different. And finally, this whole process is a must-do step for pretty much any classification model you're going to build. And this quote from Deep Lizard really just nails it. The model isn't reading, it's not thinking in English, it's just processing encoded data. Our job is to make sure that data is in the cleanest, most useful format we can possibly provide. And that kind of leaves us with a final thought, right? These little techniques, like one hot encoding, they're the basic building blocks that let us teach machines about our world, one piece at a time. So the real question is, if we can teach a computer to see a cat this way, what else can we teach it to see?